We've seen how to use truth tables to analyze whether an argument is valid or not. Now we're going to go into what's called natural deduction, which is a technique that's much more intuitive than truth tables are. Truth tables provide, however, a set of rules that we can learn from, that we can apply whenever we encounter certain patterns of premises and draw a conclusion with confidence. We're going to call them rules of inference. So we're going to use simple valid argument forms that we get from truth tables as rules of inference, which are rules that state that whenever certain kinds of premises come together, certain conclusions follow. Here's a simple example. If you encountered this in everyday life, you'll understand the conclusion right away. If it's sunny, we'll be able to go to the mountains for a hike, but if it rains, we'll have to stay home and watch TV all day. Weather Underground says there's only a 10% chance of rain tomorrow. So, what follows from that? We're going to be able to go to the mountains for a hike. That's natural deduction. That is, it's using your natural intuitive powers to draw a conclusion from premises. Here's another one. Either apples are vegetables, or else they're fruits, but they're not vegetables, so they're fruits. And here's what that would look like symbolically. If you were going to do a truth table for that, it would only take 4 lines because there's only 2 letters involved. That's called a disjunctive syllogism. But look at this one. Either apples and bananas are both vegetables, or else they're both fruit. But it's false that apples and bananas are vegetables, so they must be fruit. That's exactly the same form, but notice that it has 2 letters, A and B, apples and bananas, fruit and vegetables. Here's the main operator, this wedge, the either or. Not this case, it's not the case that apples and bananas are vegetables, so it must be the case that they're fruit. This, however, would take 16 lines on the truth table, which would be pretty ridiculous, because we can see it's exactly the same pattern as the disjunctive syllogism that we just saw on the preceding slide. That is a wedge, and the negation of one of the statements joined by the wedge yields the other statement. So here we have exactly the same thing. A wedge statement and the negation of one of the statements yields the other statement. I'm going to call that disjunctive syllogism. So we focus on the main operator of the statements to be clear on what kind of statement each one is. Here, for example, P.Q is a conjunction. That's the form. Here's an example of a conjunction. Notice that the conjuncts don't have to be simple. Here's another conjunction. The main operator is here. The conjuncts can be quite involved. The main operator in this case is here. Again, it's a conjunction. Here's a conditional. The form of any conditional is simply blank, horseshoe, blank. So here's a conditional statement. Main operator is the horseshoe. The antecedent is a compound statement. In this case, again, the conditional statement, the main operator is the horseshoe. We have a compound statement as the antecedent, compound statement as the consequent. So whenever, though, we encounter this structure, if P then Q, P is true, therefore Q is true, we'd have a valid argument, and you could look at the truth table for that and see it. That's going to be called Modus Ponens. Here's then a simple example of it. If you substituted in simple statements for each of the variables, you'd get this. If A, then C. A, therefore C. But you might substitute in compound statements like this. If either B or N, then M. Well, B or N is true, therefore M is true. That would be a case of modus ponens as well. Here would be another case of modus ponens. If L implies N, then B implies V. L does imply N, therefore B implies V. And here would be another. If H and either J or N, then L and N and L are true. H and either J or N is true, therefore N and L is true. Those are all cases of modus ponens. That is, you want to get in the habit of looking at scanning a pair of sentences or a set of sentences, looking for the main operator, and then looking to see if the other statements there contain a piece of one of these rules. You may have seen this rule once before. P implies Q, not Q, therefore not P. It's called Modus Tollens. Again, if you do a truth table for it, you'll find it's a valid argument form. What does it amount to? It amounts to a horseshoe statement or a conditional, and then negation of the consequent. And that yields the negation of the antecedent. It doesn't matter that they be simple sentences, of course. Here we go, and you notice the order isn't going to matter. Here's a negative statement, here is a conditional statement, and the consequent of this conditional statement happens to be the opposite of this. This is the negation of it. So that's going to yield tilde m dot b. Here again is a case of modus tollens. Conditional statement, here's the main operator, negation of the consequent is going to yield the negation of the whole antecedent. We talked about the disjunctive syllogism a minute ago. Here would be a simple form of that, A or B and D, not A, therefore B and D. Here would be another simple example, either K or L, or else O, but not either K or L, or neither K nor L, therefore O. And even though this is very long, it's still just a disjunctive syllogism. There's a wedge. Looking carefully, you see that this phrase is the negation of this phrase. So instead of doing a truth table that would probably be 128 lines, you can see this is immediately valid because it's a wedge plus the negation of one of the disjuncts. It's going to yield the other disjunct. P implies Q and Q implies R, so P implies R. That's called the hypothetical syllogism. What does a hypothetical syllogism, a pure hypothetical syllogism mean? It means that a term or a statement, simple or compound, is the consequent of one of our horseshoes and the antecedent of the other horseshoe, and the result is the antecedent and the consequent of the other two. That is, the common term falls out and the antecedent becomes the antecedent to the other consequent. Here's another example. You see the common phrase is B implies G, B implies G, so the conclusion is obvious. And one more. Again, the order in these things does not matter. If we have two conditional statements and the antecedent of one of them is the consequent of the other one, then we have the setup for a hypothetical syllogism. And the conclusion here is going to be K or L implies O and not C implies P. A simple rule is called simplification. It means if you have any two statements joined by a dot, then they're both true. That's what a truth table for the dot tells you in the first place. Notice, however, that here the rule is defined in such a way that it says if P and Q are true, then P is true. The rule doesn't say Q is true, it says P is true. There will be a rule in a minute that will let us switch the order of P and Q, because we do know that a dot statement is true only if both of its parts are true. Here's the dot, therefore the left-hand side is true. Another simple example, conjunction, a rule that says if you take any two statements that you know are true, you may conclude that the pair of them together with a dot is true. So this sentence is true, and this sentence is true, therefore this sentence, which just puts them together with a dot, is going to be true. It just claims they're both true. So here's our rules, modus ponens, modus tollens. Let's go through them as we rewrite them up. P implies Q, P, therefore Q. P implies Q, not Q, therefore not P. Either P or Q, not P, therefore Q. Disjunctive syllogism. P implies Q, Q implies R, so P implies R, the hypothetical syllogism. With those rules, we can actually do a proof. That is, we can say, here's a set of premises, A implies B, not A implies C or D, B is false, C is false. Therefore, D is true. We can prove that D is true, not by doing a truth table where we would lay all four of these premises out plus the conclusion, but by applying these rules. We look at these various statements, and we see, for example, that tilde B is the consequent of line 1. That means that tilde A is going to be true, because line 3 and line 1 fit the pattern called modus tollens. Now that we know tilde A is true, that's going to fit with line 2 in the pattern called modus ponens, and we're going to get a conclusion C wedge D. Now that we know C wedge D is true, and we know tilde C at line 4, it's going to follow that D is true by disjunctive syllogism. This is called natural deduction. We've reasoned from the set of premises by these simple patterns of reasoning to this conclusion D. Here again are the rules, and we'll walk through one more. E implies K implies L. F implies L implies M. Either G or E, but not G. F is true. Prove that K implies M is true. Now you might look at this in terms of the hypothetical syllogism and think, well, here's K implies L, L implies M, so doesn't K implies M just follow from that? And the answer is no. These rules only apply if the statement you're talking about is the whole line. So K implies L is a consequent. It's not a line by itself. You'd have to do modus ponens to line 1 to get K implies L as a sentence by itself. You'd have to do modus ponens to line 2 to get L implies M as a statement by itself. These pieces are going to let us do that. 3 and 4 set up a disjunctive syllogism. So E is going to be true at line 6 by disjunctive syllogism. Now, because E is true at line 6, we can say K implies L is true at line 7 by modus ponens. And since F was true at line 5, we can say L implies M is true from line 2 and 5 by modus ponens also. Now, at lines 7 and 8, we have K implies L, L implies M. That's the hypothetical syllogism. So the conclusion K implies M follows by hypothetical syllogism of 7 and 8.